Right, okay. Hi everyone, my name is Jan Zapletal and I work at the IPCC Center IT for Innovations located in Ostrava, Czech Republic. And I would like to speak about the Manycore performance of our boundary element library that we are developing. So first of all, I would like to give just a very brief overview of the library, what it is based on and what it can do. I would also like to briefly dig into the boundary element method, what it is. Basically, it is a method for discretizing partial differential equations. So I would like to comment on how it is different to, for example, the finite element method, which is widely used. Then I would like to describe the implementation actual that we use, and I will conclude with the scalability experiments performed on 3 different architectures. So as I said, boundary element method can be seen as an alternative to the finite element method. The biggest difference is that it reduces the dimension. So if you solve a problem on a 3D domain, it reduces everything to the boundary. So from 3D you get to 2D, but of course this is not for free, there's a price to pay, and the price is that you have to deal with singular surface integrals and dense matrices. The library that we are implementing is called BEM4i. It implements 3D boundary element methods, and currently what we can solve, that's Laplace equation for heat transfer or electrostatics, Helmholtz equation for wave scattering, Lamé equation for linear elasticity, and we also have a module for time-dependent wave equation. This is quite different from all the previous 3. It is a C++ library. You can interface any BLAS or LAPACK implementation. Of course, we use MKL most of the time for Intel architectures. And to overcome another disadvantage of boundary elements, that's the quadratic complexity with respect both to the number of elements. For that reason, we use the adaptive cross approximation, which reduces the complexity to log linear. The strategies that we use include SIMD vectorization for the evaluation of the singular surface integrals. Currently, we use the OpenMP pragmas. We also had a version where we use the VC library, but we abandoned that approach because the VC library doesn't seem to work well with the Intel compiler. We also use OpenMP threading for local element contributions or for the assembly of individual ACA blocks. We also have some initial implementation for MPI distribution of the ACA matrices, and we can also go massively parallel in connection with the Espresso library, which is also developed at IT for Innovations. This is in fact the finite element domain decomposition library, but if you switch from finite element to boundary elements, then you get the boundary element tiering and interconnecting method. So in this way you can make the whole cluster busy basically. But today I would like to concentrate on the single node performance of BEM4i. So how is boundary elements different to finite elements? So say that I have to solve this simple Laplace equation in 3D with given boundary data. So instead of going for the weak formulation and the finite element discretization, I start from the representation formula, which is the core for boundary elements, and it basically gives me an explicit formula for the solution. I know beforehand how the solution looks like. The problem is that I do not know these values. I do not know the solution at the boundary, because I integrate here of the boundary. I only know it on the part of the boundary, and the same for the normal derivatives. So my task, the task of the boundary element method, is to determine the missing boundary values. This formula is valid only in the volume. However, I can apply trace operators to it to transfer it to the boundary, and what I get is this set of 2 boundary integral equations, which give me some relation between the boundary data, and from these 2 equations I can determine the missing boundary data, and once I obtain them, I plug it into here, and I'm able to compute the solution inside of the computational domain. If I discretize my boundary by, say, triangles, and substitute the continuous functions by some discrete approximations, say piecewise linears, piecewise constants, I end up with these two discrete systems with the matrices V, M, K, and D. The matrices looks like this. So you can see that contrary to finite elements, first of all, these matrices are dense because these kernels here are non-local. Even though you use localized discrete functions, the kernel here is non-local. So that's the density, and the second part, the second problem is that you have to deal with these singularities here. So you have to use some more sophisticated methods for integrating. Also, in the following, I will only consider these two matrices because for the case of the Laplace equation, this matrix D is given by some simple transformation of this matrix V. So I won't comment on this. And this matrix M, this is a sparse matrix. Its action can be implemented or can be performed on the fly with no significant overhead. So I will only concentrate on these two matrices here. So there are two problems. The singularity here can be treated in two ways. First of all, you can compute this in an integral analytically and then proceed numerically. The problem is that you would have to do this again and again for each combination of this kernel and the ansatz function. This is very tedious work, and what is also quite bad is that if you have an explicit formula for this integral, this is very hard to integrate because when you analytically deal with the singularity here, it includes a lot of branching in the code. So what do? We prefer currently the numerical quadrature, which is based on a series of transformations. So what you do is that you take the product of the triangles, you understand this as a 4D object, you split it into a couple of simplices. In this way, you move the singularity to the vertex of the simplices, and then you can use the so-called Duffy substitution, which renders the integrand analytical. So at the end, you end up with smooth function here, and you integrate over 4D hypercube, and you have to sum over all of the simplices. The function here, the transformation function here, in fact maps some reference quadrature nodes from the 4D hypercube first to the set of reference triangles and then to the actual triangles, and it is different for the triangles being the same, or sharing one edge, sharing one vertex, or being completely disjoint. If you do this transformation, what you end up with is if you approximate the quadrature, you end up with this 5 nested sums. And if you program it naively, say, this translates to 4 or 5 nested for loops. The problem is that the number of quadrature points in each dimension is usually quite low. It's like 3 or 4. So the vectors in the innermost loop would be really short. So what do, or what our aim is, to collapse these 4 loops here. But first of all, as I said, we also use threading for the local element contributions. So this can be seen here, but this is not what I want to concentrate on. I would like to concentrate on the same devectorization, on the collapsing of the 4 loops. So what we do here is that we collapse the loop manually and vectorize them using the OpenMP SIMD pragmas. This is just some dummy code where we perform some work on 2 arrays. So here are 2 nested loops. Instead of that, we switch to 1 loop where we index with the same index k, which leads to data replication. But if we use only 4 quadrature nodes in each direction, and we have 4 loops, this would result in the arrays of the length 256, which is reasonable and doesn't pose any problem. Of course, all data is properly aligned so that we eliminate the pill regions, and all the quadrature point coordinates are stored in the structure of arrays format to ensure unit stride loads and stores. So if you use all of these optimizations, what you end up with is this piece of code. As I said, all the data is properly aligned. So this is, for example, the first coordinates of all quadrature nodes. In other words, the structure of arrays format. You have to switch what kind of elements you are treating. This is the case for the identical elements. For this case, there are 6 simplices that you split into. And now there are 2 main parts of this code. First of all, you need to transfer the reference quadrature points to the actual set of triangles. This is also done in finite elements. The problem here is that if you use the full assembly, you do it n squared times instead of only n times. So this has to be done efficiently as well. And even for the ACA sparsification, whose complexity is n log n, not only n, this should be done efficiently as well. And then the main part, which is the integration itself, where instead of 4 for loops, we only have 1 collapsed. And this is where you basically multiply all the weights, the Jacobian, and the singular kernel. And you do it in the SIMD manner. As I said, the transport from the reference triangle to the actual set of triangles is done in the SIMD way as well. We copy it into the result into a structure of arrays format. And the evaluation of the kernel is done in the SIMD manner as well. So we declare this function SIMD, and it can be called in the vectorized way. You may notice here that we do here something like 1 over the square root. So in theory, I could use the inf square root approximation, but the boundary elements is quite sensitive to numerical inaccuracies. So we don't use single precision arithmetic usually. We use double, and that's also why I leave the code as it is here. If you do all of this, then you make the Intel advisor happy. Basically, what we do is that we try to optimize the code until it says 100%. So this is for the computation of the actual quadrature nodes. This is for the integration itself. And one last comment before the numerical experiments, I would like to comment on the adaptive cross approximation, because its main task is to reduce the complexity from n squared to n log n. And by complexity, I mean complexity both in computational time and in memory requirements. The idea behind ACA is very similar to the idea behind FMM in n-body problems. Instead of each element talking to each other, you cluster your elements, or you put them into clusters, and then you have clusters communicating instead. Then if the clusters are close to each other, then the kernel is still not very smooth, and you have to assemble this block or this part of the matrix in full. If they are well separated, then it is enough if you only compute a couple of rows and couple of columns of this block, and that's it. Yeah, and in fact, then the matrix or the admissible block is approximated by 2 matrices, which are full, dense, but now rectangular. So this product has lower rank. Right, so the experiments were performed on a mesh with 20,000 or 80,000 surface elements for the full and AC assembly respectively. We use 4 quadrature points in each dimension, which results in the vectors of the length 256. If we use 3 only, then this number would be 81, which would result in the, not the P loop because data is aligned, but in the remainder loop. If we use 4, then 256 is divisible by 16, so there is no remainder. And in the ACA, we allow the clusters to have up to 500 elements. If there is more, then the load balancing for the assembly and for the matrix application is much harder to achieve. The problem of ACA is that you do not know beforehand, that's the word adaptive here, you do not know beforehand how many rows and columns you will have to assemble. If you would allocate it one by one, then this would totally kill the performance on KNC and KNL. So what we do is that we pre-allocate, say, 10% of the full block, and then basically you do not need any more allocation. We performed the experiments on 3 different architectures, 2 of them available at the Salomon cluster in Ostrava, so that's 2 Haswells with 24 threads in total, and AVX2 instructions. Then we have the KNC with 61 cores, and we also tested the assembly on the Endeavour cluster with the KNL processor 7210 with 64 cores. And most of the tests were performed in the flat mode, because I believe that at the time when we tested it, it was not possible to reboot into the cache mode. So first of all, we wanted to make sure that the code scales nicely with respect to the number of OpenMP threads employed. We wanted to make sure that it scales well beyond the 24 threads employed on Haswell. We knew that on Haswell this works nicely, so on 24 threads the scalability is ideal for both matrices, V and K. So this is the matrix V, single layer matrix, double layer matrix is the matrix K. If you run this natively on KNC, this is what you get, up to 61 cores. So without hyperthreading, the speed up looks very reasonable. If you continue with the hyperthreading, it helps, in fact, for the matrix V up to 3 threads per core, and you can use 4 threads per core for the matrix K. For KNL, of course, the single node performance is much better than on KNC. The scalability, again, is very good up to 64 threads, and it helps to employ 2 threads per core, at least for the matrix K. But further on, there is no scaling. But what we were more interested in was the scalability with respect to the register width. The reference times here were computed with the no-vec, no-SIMD, QNO, OpenMP SIMD compiler switches. On Salomon, on Haswell, we could test the vectorization with the SSE 4.2 instructions and AVX2 instructions. And you can see that for both matrices, the scalability or the scaling for the SSE is very good. The optimal here is 2. But AVX2 doesn't really help. We almost never reach better performance with AVX2 than with SSE 4.2 on Haswell for some reason. If you have a look at the KNC, then the optimal speedup would be 8 for double precision arithmetic. We can achieve like 3.8 for the matrix V and 5 for matrix K, which is quite nice. But what is much better is the scaling on KNL. In fact, this line is something that I don't really understand. I'm not sure how this is possible. I just recomputed the results yesterday and I got the same. So I get more than optimal scaling. I don't know why. For K, this is what I would be happy with, even though I still have better than optimal scaling for AVX2. But what is important is that, contrary to Haswell, it already helps if you switch from SSE 4.2 to AVX2. And AVX 512 is very nice. If I use only 81 points, I don't get this. I get like, I don't know, 6, 7 or something. So this is reasonable, but this is what I don't really, I don't think I understand. If I summarize, the speed up of KNL versus KNC is like 2.5, which is reasonable if I take into account the theoretical performance. KNL versus Haswell, 2.3, 1.8. OpenMP efficiency, and by OpenMP efficiency I mean that if I get the speed of 64 on any number of threads, I consider this as 100% efficiency. So for V, I get almost 100, for Q 115. Again, the SIMD efficiency 124%. For K, this looks good. So that was the full assembly. That's completely compute bound. ACA assembly is more say more complicated, but on Haswell it again performs nicely up to 24 threads for both matrices. On KNC, again quite nice, up to 61 threads, and helps to introduce the hyperthreading again, so you get more than 61 speed up if you use hyperthreading. On KNL, again single thread performance much better than KNC, but here we are not able to achieve the 64 speed up. So there's definitely some more work to be done, and I think that we have already tested this assembly in the cache mode and it helps, but I don't have the results here, so I'm not sure what speed up we reach actually. Again, the SIMD scalability on Haswell, very similar results to the full assembly. On KNC, almost 3 and 3.5 for both matrices, and on KNL again the vectorization works nicely, but still I get more than optimal results here, especially for the AVX2 and SSE 4.2, and I get something that I would expect more for the matrix K here. Again, if I summarize, KNL versus KNC, 2 and 2.9 speed up, KNL versus Haswell, 2.6, 1.4, OpenMP efficiency about 90%, and SIMD efficiency 100% for V, and 67% for K, which I still consider reasonable. And the last thing that I would like to comment on, if you assemble the matrix not in full but in the ACA mode, you cannot use direct solvers to solve the system. You have to use some iterative solvers, say conjugate gradients. So you also have to implement the matrix multiplication efficiently, because if you can assemble it efficiently and cannot multiply, then it is good for nothing. The performance on Haswell is not very satisfactory. On 24 threads we get only the speed up of 8. The problem with ACA is that it creates blocks in the matrix, but the blocks are not contiguous. In fact, this is just a virtual block. The block basically means that you take some rows of the matrix and some columns of the global matrix. So the rows and columns are spread in the global matrix, and if you perform the multiplication, then the global vector that you multiply, basically, well, what we do is that we distribute the blocks among OpenMP threads, and each thread performs the localized multiplication. But before it can do so, it has to gather the relevant data from the global vector. So there is definitely not unit stride, and there is even no, so it is a very irregular gather. And then when you multiply, you have to write into the target vector, which is again a non-regular access. So on Haswell, this doesn't really perform well. What I was really surprised about was this KNC. We get up to 120 speed up if we employ all cores. So the scalability looks really, really nice, and we don't get these results even on KNL. And this is the only case where we use the KNL in the cache mode, because this is the test that we performed a couple of days ago, and here we can get a speed up of 68, so bigger than 64. If I didn't use the cache mode, we also tried it in the flat mode without the MCD RAM, and the only difference basically would be that these two last times would not be better than 2 hyperthreads per core. Right, so to sum up, KNL versus KNC 1.6 versus Haswell 2.6, OpenMP efficiency 107%, but what we want to do, of course, is to optimize this for Haswell as well. I don't comment here on the vectorization because the local multiplication is performed by MKL, which is vectorized by itself. So what we learned during the mic optimization, it has been mentioned here many times. In fact, when we optimized for mic and then transferred the code back to CPU, we immediately gained performance, of course. We found out that SIMD processing on KNL is much more efficient than on the KNC architecture and Haswell. What we have problem with since Intel compiler 2016 update 3, we cannot use O3 flag because it causes troubles. It is way too aggressive. It wants to vectorize loops that should not be vectorized. It assumes that some data is aligned even though it is not aligned, at least in our code. On the other hand, what we found useful was Intel Advisor. As you could see, Intel compiler reports and Alinea DDT for debugging. What we are currently working on, what we want to make better, is to make the load balancing of ACA matrix application perform better, especially on Haswell, on multi-core. What I didn't mention is that we also allow for offload mode for the assembly. This is very dirty code. So what I would like to do is to have the offload code in a more object-oriented fashion. The problem a bit is that I haven't seen any tutorial on the offloading with C++ codes. It's only Fortran or pure C. The problem that we have, for example, if we offload in some member function, the offload pragma for some reason automatically transfers the this pointer as an in-out variable, and then in the pragma body, in the offload body, the this pointer is somehow changed on mic, then transferred back, and you get segfault. So what we have to do for every offload is that we specify this pointer as in variable only. No idea if this is a bug or feature. I don't know. Maybe we could switch from the Intel Leo offload pragmas to the OpenMP 4.5 standard. We haven't tried, so this might be the way. I don't know. And what I would also do is to vectorize a supporting function in the whole library, like working with the mesh and stuff like that. Yeah, and that's all I want to say. So thank you for your attention.
Questions, if anybody has any. Okay, so a simple, oh, we do have one, okay.
Why in some cases hardware threads give some speed up, little speed up, but in some cases they don't provide any speed up?
So I don't know, really. I'm not even sure how I should investigate this.
Second question on how you measured speed up on your vectorized loops. It's advisor from advisor or with?
No, there was our timing inside of the code. We were inspired by Intel performing the test. We usually do 4 measurements. We discard the first and then compute the average. So I don't know if you have an idea why we get the speed up of 10, because even the 8 is better than it should be, because you have to take into account the frequency, which is 15% lower than for the scalar instruction. So this is even worse. No idea.
Okay, so I do have a question. So you said that there were some issues you had with 2016 update 3 and 03. Did you find a bug?
Yes, so I found out that in one loop, which was not vectorized in update 2, it became vectorized in update 3, and it assumed probably that some data is aligned. So I got segfault there.
Share that test case with us in-house.
I will.
Okay, so that is the end of the talks for today. So thank you all for your attention, and see you tomorrow.